Thanks for introduction.
The talk is about lower bound for succinct range minimum query. This is a joint work with Yuhua Chen from Princeton University. Range minimum query, aka RMQ, is a classical data structure problem. Given an array of numbers, the queries may give some ranges and ask the minimum over the ranges. For example, the minimum between the third element and the eighth element in this array is 1. However, in this work, we study a variant of RMQ, which asks for the index of the minimum. In this case, the answer for query RMQ of 3 and 8 is 4 rather than 1. The RMQ is a fundamental problem which has numerous applications in computer science, including text processing, graph problems, and infobiometrics. In particular, RMQ is a critical component in aid of the application of the longest common prefixes array of suffix array. RMQ is equivalent with the lowest common ancestor problem for binary trees. The equivalence is established via a structure named Cartesian tree. Cartesian tree is introduced by Villamy in 1980. Given an array of numbers, the Cartesian tree with respect to the array can be constructed recursively as follows. At first, we take the minimum over the whole array as the root. Then, the array is broken into 2 subarrays by the root. We construct Cartesian trees with respect to the 2 subarrays recursively and let them be the left and the right subtrees of the root, respectively. With Cartesian tree, the RMQ can be reduced to lowest common ancestor problem in the tree. For example, the lowest common ancestor of 12 and 20 is 10, which is a minimum of the range from 6th element to 8th element. It is easy to say that one cannot compare 3 and 5 in this array with RMQ, since there is a 1 in between. Similarly, we cannot compare any pair of elements which are separated by 1. It is also not hard to say that, given all the answers of range minimum queries, we can construct a unique Cartesian tree. And given any Cartesian tree, we can construct all the answers of range minimum queries. By this observation, one may conclude that the input is in fact a binary tree. RMQ has a classic textbook solution, which uses open space and constant time. As we argued before, the input is in fact a binary tree, and the size of input universe is a Catenna number. The logarithm of nth Catenna number is 2n minus O log n. Therefore, the truly linear space should be On bits and using On over log n words if the word size is log n. Consequently, we choose the uniform distribution over all n-node binary trees as the hard distribution to prove the lower bound. It is because the setting maximizes the input entropy and matches the space benchmark. In 2007, Sadakane presented the first linear space data structure for RMQ. Later, Fisher and Huygens presented the first succinct data structure for RMQ. A data structure is called succinct data structure if the space cost is close to the minimum space to store the database. The extra space cost is called redundancy. 3 years later, Navarro and Sadakane improved the space upper bound to 2n plus n over polylog n bits. Naturally, two questions come to our mind. First, is there a lower bound for RMQ? Second, does the state-of-the-art data structure with constant time have an optimal space upper bound? In this work, we present the first lower bound for RMQ. Our lower bound shows that the state-of-the-art algorithm is optimal in the regime of constant time. Before introducing our approach to proving lower bound for RMQ, I would like to introduce the computational model. The CellPro model is introduced by Andrew Yao in 1981. It is very similar to the famous RAM model. In the CellPro model, operations are free, except memory access. In the CellPro model, a data structure is interpreted as a table of memory cells. The interaction with data structure is modeled as a procedure of cell probing. Given a query X, the CPU chooses a memory cell C1 with its unlimited computational power in the first round. The CPU retrieves the content of C1 by cell probing. With the content of C1 and the query X, the CPU chooses a new memory cell C2 in the second round. This procedure keeps going on and on. After T rounds, the CPU has collected enough information and comes up with its output with all the known information. Now, let's move to the proof sketch. In fact, we prove a lower bound for a problem named PretZ. We believe PretZ characterizes the hardness of RMQ. At first, we reduce PretZ to RMQ. Then, we show lower bound for PretZ. In order to do this, our strategy is a new variant of round elimination on carefully choosing hard queries. We use a new series of ideas and proofs to show the round elimination is feasible. The classical round elimination is developed by Petrescu and Viola in 2010. Their proof uses a new variant of round elimination in a tweaked CellPro model. In this model, a data structure may use extra p-published bits besides the minimum space to store the database. The published bits may arbitrarily depend on the database. It also can be accessed by CPU for free. Of course, if there is a data structure which solves RMQ using p bits of redundancy and t time, then there is a data structure which solves RMQ using p published bits and t time in the published bits model. We can publish the p bits of redundancy. Petrescu and Viola argue that for data structure using p published bits and t time, we can publish p times polylog n cells to save 1 time of memory access for many queries. By recursively applying this argument, We obtain a data structure that uses some published bits, but does not access any memory cell. So, the number of published bits in the final data structure cannot be less than the information theoretical lower bound. The key argument lies in publishing more bits and saving memory access. It is feasible since the answers of queries are correlated. We evenly choose a set of queries Q1. Then, if most of queries do not probe the cells probed by Q1, with good probability, we show two consequences. First, a random set of Q2 do not probe the cells probed by Q1. Secondly, lots of information is both contained in the answers of Q1 and Q2. The information is both contained in the cells probed by Q1 and Q2 as well, since the CPU can recover the answers of Q1, Q2 with the cells. However, Q2 don't probe the cells probed by Q1, which means the bits are wasted. So, we can remove 5p bits by compressing from the data structure. In the end, we have a too good to be true representation of the database. Unfortunately, the Q2 argument does not work for RMQ. Why is that? Because the argument works for the average case lower bound, but we believe that RMQ has efficient average case solution. Hence, we move our concern to a set of hard queries, which are correlated with the database, and we apply round elimination on the hard queries only. Since the hard queries are highly correlated with database, we cannot use some cells probed by some specified hard queries to compress the cells probed by Q1. It is too expensive to write down hard queries. In order to get over this, we develop a more powerful lemma. We show that for the properly choosing queries QPub, if many hard queries do not probe the cells probed by QPub, the cells that are not probed by QPub contain lots of information about the answers of QPub. With this lemma, we use the same idea to compress the data structure. All the three steps are non-trivial for pretty Z. We will elaborate them later. First of all, we introduce the pretty Z problem. Note that we are dealing with succinct data structures, so we have to carefully control the increment of space cost in reducing.
Okay, so Sean can okay here she'll try yeah, okay. Yeah, you can start from now on.
Okay. The starting point is very simple. We observe that the RMQ becomes predictive search if one end of the query range is fixed. For example, if the left end of the queries are fixed to 1. This problem becomes a predictive search with database 1, 4, 6, and 9. In particular, the answer of any query with right end that is less than 4 will be 1. So it suffices to prove lower bound. It suffices to prove lower bound for the underlying predictive search. However, an obstacle emerges immediately. The underlying predictive search has very low entropy under our reduction and distribution. A simple reduction introduces unacceptably large redundancy, which result any non-trivial lower bound. Our patch is simple. We force the algorithms to waste space on the dummy information, which is the Z. Formally speaking, the database of pretty Z consists of D subproblems and a large integer Z. Each of the subproblems is a set of U distinct elements from a universe of size B. Pretty Z requires the data structures to answer two kinds of queries: execute perimeter search in some subproblem or return the Z. We care about the time-space trade-off between the time cost on perimeter search and the space cost in total. Note that the time complexity on query Z can be arbitrarily large. We then embed the database of pretty Z into the Cartesian tree to reduce it to RMQ. We get the subproblems into pairs. One pair of subproblems is embedded into a small tree which has 2B plus 3 nodes. The 2U data points in the databases are embedded into these two paths. And the other elements from the universe are embedded into the subtrees. To answer the perimeter search X in subproblem I, we just return the lowest common ancestor of the dummy node corresponding to subproblem I and the node corresponding to element X in subproblem I. Recall that the database for RMQ is one single binary tree, so we merge the D/2 small trees into one. Note that the LCA oracle still solves the perimeter search, since the merge does not change the in-order traversal. Then we let Z encode remaining information of the tree. That is the way we merge the D/2 small trees together with the structures of the subtrees. To answer the query Z, we retrieve the whole tree and compute the Z by range minimum queries. Query Z forces the data structure to waste space on the Z. The trick overcomes the By properly choosing the parameters, we show that if there exists a data structure for RMQ using R bits of redundancy and T times, then there exists a data structure for pretty Z using OR log N bits of redundancy and T time. We prove this lower bound for pretty Z. By our settings, the lower bound for pretty Z implies the desired lower bound for RMQ. So it suffices to show this lower bound for pretty Z. We show the overlap between the cells proved by hard queries and QPub should be large. By recursively applying the round elimination lemma, we obtain a too good to be true representation, which implies a lower bound for pretty Z. By our reduction, we obtain the desired lower bound for RMQ. We elaborated the 3 steps for proving round elimination lemma in the following slides. At first, we fix a good set of queries QPub. We show that the answers of QPub contains lots of information about the database. Then, if there are too many hard queries which do not probe the cells probed by QPub, we show that the cells which are not probed by QPub contain lots of information about the answers of QPub. Finally, we compress the cells probed by QPub with the cells which are not probed by QPub. In the end, we have a too good to be true representation of the database. Keep in mind that the answers of QPub have to have at least p bits of entropy. Otherwise, we cannot obtain a too good to be true representation by assuming that many hard queries do not prove the sales proved by QPub. Picking a good set of queries is not an easy task under our distribution. We are going to execute round elimination recursively, so we are going to publish the sales proved by QPub in each round of round elimination. If we pick too many queries, we would publish too many bits in each round. In that scenario, we cannot eliminate many rounds, since the number of published bits in the end is limited. It turns out that we cannot prove a good lower bound. If we pick the queries obviously, that is exactly how Petrescu and Viola did. The answers of the choosing queries contain only a few of information. In that scenario, the number of published bits will be squared after each round of round elimination. It turns out that we can merely prove a very bad lower bound. Our approach is picking QPub too adaptively. We pay extra p log n bits to specify the QPub. It's okay, since what we save is more than what we pay. Let's move our concern to a sub-problem. Imagine that we put the B numbers of the universe on a line. The black dots are the data points. We break the D sub-problems into P blocks. Every block is an interval on the line. Every block contains M data points. Of course, the lengths of the blocks are various. What we want are the blocks of length M squared. Finally, we pick queries evenly in the good blocks. We do it in this way because we believe that the good blocks have the same structure with the sub-problems. For a random unknown binary tree, the two paths have roughly square root n nodes. If we evenly pick k queries in a sub-problem, the entropy of the answers is roughly square root n. It can be checked that many blocks are good, and the answers of QPub reveal lots of information in good blocks. Here we choose E to measure the revealed information. E is an array of bits. Emerging the queries in QPub. We care about if there is data point in between two adjacent queries. For example, there is no data point in between, so in E, the bit corresponding to this interval is 0. In contrast, the bit corresponding to this interval is 1. Because many blocks are good, because the answers of QPub reveal lots of information in good block, and because the blocks are mutually independent, we conclude that we have picked a good set of queries. The E reveals lots of information about the database, and the information is contained in the answers of QPub. The next step is to show that the set of cells which are not proved by QPub contains lots of information about the answers of QPub if many hard queries do not prove the cells proved by QPub. Given the set of cells which are not proved by QPub, we can enumerate all the queries and try to answer the queries with the set of cells. Recall that we choose the queries on all input data points as the hard queries. If there are many hard queries which do not probe the cells probed by QPub, we can recover many data points from the cells which are not probed by QPub. Assume we can recover at least 1 minus epsilon fraction of the data points. Then we can fully recover the E with an extra short auxiliary bit string. Recall the definition of array E. QPub breaks the universes into small intervals, and the array E encodes all the intervals that contain at least one data point. On the other hand, given the cells which are not probed by QPub, we can recover at least 1 minus epsilon fraction of data points. Consequently, we know a fraction of non-empty intervals. To fully recover array E with the known data points E, our approach is writing down all the unknown and non-empty intervals. A way to encode a set of numbers is to sort them in the increasing order and to write down the differences. We encode the unknown non-empty intervals in the same way. Let's focus on some good block. The small intervals on a line can be considered as points on a line. We are interested in the non-empty intervals. We let I1, I2, I3 be the indexes of non-empty intervals. For the unknown non-empty intervals, at first, we write down a number to inform the non-empty interval which precedes the unknown one. Then, we write down the distance between the known interval and the unknown interval. For example, we write down a number 3 to inform that the next unknown interval succeeds the second non-empty interval. Then, we write down a number 1 to inform the next unknown interval. It has index 3. Now, the non-empty interval, which has index 3, becomes a known interval. So, we write down number 1 to inform the next unknown interval succeeds the third non-empty interval, and we write down number 1, 2, 3, 4 to inform that the next unknown interval has index 3. To show the code word is not too long, we involve two lemmas. The first one shows that there are not too many intervals which are unknown and non-empty. The second one shows that the non-empty adjacent interval pairs are close. Both lemmas are proven by carefully analyzing the input distribution. By putting everything together, we conclude that the auxiliary bit string is short. Finally, the last step. Recall our compression procedure. After the first step, we write down all the cells which are not probed by QPub. Then we write down the auxiliary bits. Finally, we compress the cells probed by QPub. To make it happen, we have to know the addresses of the cells which are not probed by QPub. We cannot just write the addresses down because the query algorithm is fully adaptive. In other words, the addresses may reveal lots of information about the database, which may easily bypass this, or one may easily bypass this difficulty by assuming the query algorithm is non-adaptive. That is to say, the set of probed cells depends only on the query. The solution is inspired by one simple observation. Recall the interaction between the CPU and the memory. The addresses of the cell proved in else round is fixed as long as all the L-1 previous cells are fixed. Then we can choose a good L such that the set of cells proved in else round reveals lots of information about the answers of QPAB. In this way, we achieve some kind of non-adaptivity. More specifically, we write down the first L-1 cells proved by QPAB. So we know the addresses of the else cells automatically. Then we compress the else cells proved by QPAB. Now we are ready to show the compression procedure. At the first step, we write down everything except the cells proved in else round by QPAB. In order to do so, we write down the p-published bits and write down some bits to inform QPAB. Then write down the cells proved in the first L-1 rounds by QPAB, followed by the contents of the rest of cells, except the cells we want to compress. In the second step, we write down the auxiliary bits to recover E. Finally, we compress the cells proved by QPAB in else round, given E. We assume the new published bits save at most delta probe in expectation. By putting everything together, we conclude that the overlap has to be large to avoid contradiction. In conclusion, we prove first lower bound for RMQ. Our lower bound shows that the state-of-the-art algorithm is optimal in the regime of constant time. The lower bound is proven by reducing from pre-Z. We employ a new idea to space the space loss in reducing for proving lower bound. We find new ways of proving worst-case lower bound and attacking fully adaptivity to prove lower bound for pre-Z. There are some interesting open problems. Can we close the gap between the lower bound and the upper bound for range minimum queries in general case? And is there a more powerful tool to deal with the adaptivity? That's all. Thanks for listening.
Okay, thanks, Mio, for the nice talk. So, yeah, actually, I got a question, but yeah, the question is actually what you mentioned in the last page, the lower bound for pre-Z being proved or it's proven to be tight. I think it's not tight, right?
Yes.
And like any, well, then the next question would be like any like intuition for like showing a tight bond, like.
Sorry.
Like,
can you speak it in? I can't hear you clearly.
Oh, really? So can you hear me now? Hello?
Okay, it's better.
Okay. So yeah, the lower bound for. So what do you think? Like, can the lower bound part be improved, or you think it's not the lower bound part? It's on the other side.
Sorry, I still can't hear you clearly.
Okay. So I'll try to move to another place and try to because yes, so many people talking there. So can you hear me now?
Okay.
So the question is about yeah, you mentioned that the lower bound part is not tight. The lower bound is not tight. So like any idea for like proof like showing a tight lower bound? Like any kind of intuition, like any initial ideas for?
Well,
from your understanding.
The main barrier here is fully adaptivity. You say that we only compress only 1/t fraction of the cells. So our approach to deal with the fully adaptivity lost. You see our lower bound is n over log n to t squared log squared no t squared. Okay, so this we lost 1/t. The 1/t. If the algorithm is not adaptive, so we can prove a lower bound of n over log n to t, which I believe it will be the optimal upper bound. But the way we deal with the fully adaptivity lost too many information in our compression procedure.
I see. Okay. There's another question. You see, will it make a difference if the encoding steps are exchanged?
Can you say it again?
Sure. Will it make a difference if the encoding steps are exchanged?
Encoding
steps, yeah.
No, I don't think it will make any difference.
Okay. Okay, thanks. So if there's no more questions, then let's thank Mimo again. And that concludes Mimo's talk and our talks in the afternoon. Thank you.